In this video, we will see how to find out maximum bending moment and bending stress induced in case of overhanging beam. Now, the overhanging beam is shown over here. It is having the left-hand side overhang of 0.5 meter. Now, we have to find out the maximum bending stress induced in the shaft of 100 mm diameter. So, the cross section of this beam is circular and the diameter is 100 mm. The shaft is supported in the bearings at A and B. So here at A and B, the shaft is supported and it supports only the vertical forces. So these are the vertical forces which are acting 10 kilonewton and 20 kilonewton. So to support this downward acting force, the reaction will act in the upward direction. The first step is to calculate the value of these beam reactions RA and RB. Now we have to apply the condition of equilibrium. So the first condition of equilibrium is summation of forces in y direction is equal to 0. Upward forces, they are considered as positive and downward forces, they are considered as negative. So you can say that RA and RB, they are acting in the upward direction, so they are positive. Whereas 10 kilonewton point load and this 20 kilonewton point load, it is acting in the downward direction and hence it is negative. So therefore, Ra plus Rb will be equal to 30 kilonewton. Let us call this as our equation number 1. Now the important part is we have to find out the moments. So summation of moment about A is equal to 0. So we are taking moment about this point A. Correct? We have to take the moment about any of the supports, either A or B. So we are taking moment about this particular point A. Now this RB will produce anti-clockwise moment about point A and hence it is negative. The perpendicular distance between B and A is 1.4. From B up to A it is 1 plus 0.4, that is 1.4, and as it is an anti-clockwise moment it is negative. This 20 kilonewton downward acting force will produce clockwise moment about point A. So 20 into 0.4, clockwise moment is positive, so this is positive sign that we have used. This 10 kilonewton point load will produce anti-clockwise moment about A. The distance between C and A is 0.5 meter, and as it is anti-clockwise it is negative, so it is minus 10 into 0.5, and that summation must be equal to 0 for the equilibrium. Now the value of 20 into 0.4 minus 10 into 0.5 is 3, and we have transferred this negative term minus RB into 1.4 on the other side, so it will become positive. Divide this 3 by 1.4 so that we will get the value of RB as 2.142 kilonewton. Now substitute this value in equation 1. So from equation 1 we can say that RA will be equal to 30 minus RB. Substitute the value of RB, it is 2.142. So we can say that the value of RA is 27.858 kilonewton. Now we have obtained these particular values RA and RB. Now we will draw the shear force diagram over here. The conventions which we have used for shear force diagram is upward forces are positive and downward forces, they are considered as negative. Shear force at point C is minus 10 kilonewton because it is acting in the downward direction. Shear force at A left, just at the left of A without considering this reaction RA, is also minus 10 kilonewton because there is no other force that is acting between C and A. But exactly at point A there is a upward acting reaction, so minus 10 plus 27.858, that is 17.858 kilonewton. Shear force at D left without considering this 20 kilonewton, so from A to D there is no other force that is acting, so whatever is the force that is acting at point A, the same will be acting at point D left, just left of the D. Now exactly at D, to this 17.858 there will be a downward acting 20 kilonewton force will get added, so that value comes out to be minus 2.142 kilonewton. Again from D up to just left of B no other force is acting, so B left will also have the same shear force as that of D, that is minus 2.142 kilonewton. Now exactly at point B there is a upward acting reaction. Upward forces are considered as positive, so minus 2.142 plus this RB, that is 2.142 kilonewton. So total will be 0 kilonewton. Now we'll draw the shear force diagram over here. So you can see the various values which we have obtained are represented over here. Shear force at C minus 10, A left minus 10, exactly at A 17.858, D left it is 17.858, exactly at point D it is minus 2.142 kilonewton, remains same up to B left and becomes 0 exactly at point B. Now we have to find out the value of maximum bending moment. Now at the end of the beam, that is at point C and at point B, bending moment is always 0. So those values are indicated over here. Now we have to find out bending moment at point A. Consider all the forces which are acting on the left hand side of A. So there is only 10 kilonewton force and it is producing anti-clockwise moment. 10 into 0.5, that is indicated over here, that is minus 5 kilonewton meter. Now we have to find out bending moment at point D. Consider all the forces which are acting on the left hand side of D, that is this 10 kilonewton and this 27.858 kilonewton. Now this 10 kilonewton will produce again anti-clockwise moment. So it is indicated by this arrow. Distance between C and D is 0.5 plus 0.4, that is 0.9. So it is minus 10 into 0.9. Anti-clockwise moments are considered as negative. So minus 10 into 0.9. This RA, which is acting in the upward direction, will produce clockwise moment about D. So 27.858 into perpendicular distance between A and D is 0.4 meter. So 27.858 into 0.4. This will give us the value of 2.1432 kilonewton meter. Using this, we have to draw the bending moment diagram. Now, as you can see over here, the maximum value of the bending moment is minus 5 kilonewton meter. Now, neglecting the sign, correct, we'll take into consideration the maximum bending moment as 5 kilonewton meter. First, convert kilonewton into newton. So, we have multiplied by 10 raised to 3. Again, convert meter into mm. So, again, we have multiplied by 10 raised to 3. So, total value will be 5 into 10 raised to 6 Newton mm. Now the cross section of the beam is circular. So we can say that bending stress is given by M max divided by ZXX, where M max is maximum bending moment and ZXX is section modulus. For circular section, ZXX is given by pi by 32 d cube. Substitute the values. So maximum bending moment is 5 into 10 raised to 6 Newton mm. Now this denominator of the denominator, it will go in the numerator. So bending stress will be equal to 32 into 5 into 10 raised to 6 divided by pi into 100 raised to 3. So the calculation will yield us the value of, the calculation will give us the value of bending stress as 50.929 Newton per mm square or MPa. So in this way, we can find out the value of maximum bending moment and hence the corresponding value of maximum bending stress. Thank you very much for watching.